Hi everyone, it's a pleasure to be here to present our work, HVAC, Invading Classifier-based Defenses in Hidden Voice Attacks. My name is Yu, a second-year PhD student at the University of Tennessee, Knoxville. This is a collaborative work with Xiang Yu and Dr. Yu at Shanghai Jiao Tong University, Katie and Dr. Saxena at the University of Alabama, Birmingham, my Dr. Liu at the University of Tennessee, and Dr. Chen at Rutgers University. Automatic speech recognition systems, also known as ASR systems, have been applied in many commercial products such as Amazon Echo, Google Home, and Apple HomePod. In a voice control smart home, they can almost control everything, such as help us unlock or lock the front door, turn or dim the lights, and play our favorite albums. Besides, they are also popular in voice control smart vehicles, which serve as part of the autonomous driving as well as vehicle networking. However, the rapid deployment of them also brings upon concerns of the potential security vulnerability. Many works have shown that deep neural networks, such as DNNs, which serve as the computational core of ASR systems, are vulnerable against hidden voice attacks. An adversary could generate a noise-like audio sample, which is identical to humans, but can be correctly recognized by ASR systems. A malicious adversary could let your phone browse to a malicious website without your attention. Moreover, a hacker may transfer your money to another account using a fake voice command. This could lead to a severe consequence. However, they can be easily detected and defeated using a machine learning-based defense classifier. Since hidden voice commands sound like noises, they would exhibit significantly different patterns compared with normal human voice. A simple logistic regression classifier could distinguish hidden voice command from normal human voices with a 99.8% true positive rate and only a 0.2% false positive rate. In the presence of a defense classifier, the hidden voice command will be correctly detected, thereby being rejected by the ASR system. In this paper, we take one step further and explore how hard to defeat the classifier-based defenses and launch an advanced hidden voice attack to bypass the classifier-based defenses. We propose a HVAC hidden voice attack in the presence of classifier, a more powerful hidden voice attack that can circumvent existing learning-based defense classifiers while remaining unintelligible to humans, but could be recognized by ASR systems. Through elaborately mixing the signals of the hidden voice command and its corresponding normal command, the adversary could push the acoustic features of the HVAC command towards the features of the normal human voice, potentially making the defense classifiers yield false predictions. Existing works have shown that an adversary could generate a hidden voice command from a normal speech by preserving most of the MFCC features. The normal command is sent to the audio mangler, where the MFCC features of the given command are extracted. Then, the MFCC features are converted back to an audio sample through inverse MFCC operation, which produces a candidate voice command. Therefore, the candidate voice command shares the same MFCC features compared with the normal command, which will tend to make ASR systems output the same transcription. Meanwhile, it only preserves the features that are useful for machine understanding, while features contributing to human perception are discarded. If the candidate command can be recognized by the given ASR system correctly, and also cannot be understood by humans at the same time, then the command is a valid hidden voice command. Otherwise, it needs to be reproduced by adjusting the 5 MFCC parameters in the audio mangler until it can pass the 2 tests in the command sector. However, as aforementioned, this work can be easily defeated using a pre-trained machine learning-based defense classifier. To pass the defense classifier, we propose a generic audio processing flow that can generate HVAC commands from any normal commands. There are 2 main components, including HVAC command generation, which generates the candidate HVAC commands, and also human perception mask, which is used to further enhance the intelligibility of the HVAC commands. First, an adversary could create a normal command using a text-to-speech engine. Next, as aforementioned, the adversary generates the corresponding hidden voice command through tuning the 5 MFCC parameters during the process of MFCC extraction and the inverse MFCC, which is similar to the existing studies. In this step, 5 MFCC parameters are used to regulate the granularity of the extracted features. They are initialized with random values at the beginning and then iteratively adjusted according to whether the command can be recognized by the ASR systems. Meanwhile, a syllabus detection algorithm is implemented to detect the speech parts and the non-speech parts of the normal command. Compared with the non-speech parts, speech parts consist of multiple audio segments, and each segment represents a single syllable. Specifically, the adversary uses a syllabus segmentation algorithm in which the key idea is to find segments in the audio sample which contains a relatively larger power density than a predefined threshold. This figure represents an example of implementing the algorithm on a normal command, which is OK Google as the transcription. The detected syllables are labeled with red rectangles. We can observe that the detected syllabus segments contain relatively larger energy and match the voice activity in the audio sample. The adversary then fuses the normal command and the hidden voice command in command fusion. Through command fusion, parts of the HVAC command preserve the characteristics of the normal command, which makes the traditional classifier-based defenses that use acoustic features from the whole audio hard to distinguish it from the normal commands. Since the non-speech part won't affect machine understanding and human perception, they are directly copied from the normal command, and the speech part is a combination of the two audio samples. Preserving the whole non-speech part from the normal command would maximize the proportion of the characteristics inherent from it in the HVAC command. The parameter k indicates the proportion of the hidden voice command in the HVAC command. A larger k means more features from the hidden voice command are preserved, and vice versa. Same with the 5 MFCC parameters, k is also initialized with a random number at the beginning of the command generation. After command fusion, to further downgrade the human intelligibility, the adversary would add a human perception mask to make it distorted and lose consistency. There are 4 human perception mask parameters that control the scale of the audio distortion. A more distorted HVAC command would be harder for humans to understand, but it may also let the ASR systems couldn't recognize it. Therefore, the adversary needs to test whether the HVAC command can be recognized by the target ASR system and adjust the 4 parameters accordingly. The human perception mask contains 3 components: audio tuning, pitch shifting, and time domain inversion. When the same speech is spoken at a faster rate, it would be harder for humans to understand. However, the frequency spectrum will remain mostly the same and won't largely affect the machine understanding. Also, scaling up the pitch of the audio would make the command shriller and less likely to be regarded as a human voice. We first resample the audio to a new frequency and further rescales the time axis of the resampled audio to compensate for the reduced length while ensuring the original audio speed. Finally, it's time domain inversion, which is a sliding window-based algorithm, which inverses the audio signal in time domain in each sliding window. There is no overlap between successive windows, and the size of the windows is predefined in the parameter set. This would preserve the frequency characteristics in each window, but makes the audio signal discontinuous and perturbed in the time domain, which makes it harder for humans to understand. We select 15 speech commands for evaluation, which exhibits a series of potential political threats. Some examples are call 911, take a picture, and wake me up at 8 a.m. We consider the most realistic attack scenario, where the HVAC commands are played over the air to attack the ASR systems. In particular, the HVAC commands are played in 3 different inverse setups, using 2 models of loudspeakers and received by 3 different voice assistants. Amazon Echo and Google Home are chosen as the victim voice assistants, where HVAC commands are played 1 meter away. We also use an external microphone to emulate the built-in microphones of smart home appliance, and it is placed 1 to 3 meters away from the loudspeaker. We first test whether the HVAC commands could bypass defense classifiers trained using normal commands and hidden voice commands. We use 4 different machine learning algorithms, and the results are shown in Table 1. We found that nearly all of our HVAC commands can bypass the existing state-of-the-art classifiers. We further test whether our HVAC commands on a stronger defense classifier that is trained directly with HVAC commands and normal commands. We use 1,000 recorded HVAC samples are used as the testing set, and the results are shown in Table 2. We can see even if the training set involves the HVAC commands, due to their acoustic features share a similar pattern compared with normal commands, it would be hard for the classifiers to distinguish them from normal commands. When using the gradient boosting classifier, we can increase the success rate of bypassing the defense classifiers to at most 96.3%. This is much higher compared with existing works, which is as low as 0.2%. The convincing results demonstrate that our HVAC attacks cannot be defeated, even if the ASR systems is able to get access to our attack flow and gather a large amount of training data. We further evaluate whether our HVAC commands can be correctly recognized by ASR systems. For each switch command, we play the generated HVAC command 20 times, resulting in a total of 300 samples recorded in each setup. The average ASR recognition accuracy of these 20 samples are used as the evaluation matrix. We achieve an average of 89.3% on Amazon Echo and 91.9% on Google Home. The results of using an external microphone to record the HVAC command at a 1 meter distance from the loudspeaker is 91.7%, which is similar to the results obtained from 2 smart speakers. To further demonstrate the robustness of these commands, we extend the distance between the loudspeaker and the microphone to at most 3 meters. Specifically, we achieve an average accuracy of 91.8% at 1.5 meters, 81.9% at 2 meters, 81.4% at 2.5 meters, and 74.6% at 3 meters. With the increase of the distance between the loudspeaker and the microphone, the average ASR accuracy tends to drop. This is because the sound level of the played commands would decrease at the microphone side. Meanwhile, a larger distortion would be introduced in the prolonged transmission channel. However, even if we increase the transmission distance up to 3 meters, we still achieve an accuracy of 74.6%, of 74.6% accuracy, which means that most of the HVAC commands can be correctly recognized by the ASR systems. To defend against our attacks, one possible approach is liveness detection, where we train a classifier to detect whether the voice sample comes from a human speaker or is replayed by a loudspeaker. Another way is to leverage the physical features, such as the vibration features, to distinguish between the hidden voice command and the normal command. We leave this as our future works. In general, this paper proposed a more advanced hidden voice attack, HVAC, which can bypass the existing defense classifiers while preserving all the essential characteristics of hidden voice attacks. We proposed a fusion-based method to combine the normal sample and corresponding HVAC command as a hybrid command for bypassing these defense classifiers. In addition, several acoustic parameters, including speed, pitch, etc., are further tuned to make the command even harder to be understood by human listeners. It can still be tuned to make it can still be recognized by machines. Extensive physical over-the-air experiments on different smart speakers demonstrated that our proposed HVAC commands can bypass existing defense classifiers while still maintaining a low intelligibility to humans and a high recognition accuracy for ASR systems. So thanks for your listening, and I'm glad to take any questions.